work and energy in electrostatic fields. But before that, we'll look at two equations. One is the Poisson equation and the other is Laplace equation. The Poisson equation, you can just derive it. Derive it yourself. You have divergence of electric field is charge density per epsilon naught, volume charge density by epsilon naught. And then you have electric field is equal to the negative of gradient of your potential field. If you substitute this one in this one, you'll get this one. So that is fine. And when your volume charge density is 0, you'll get your Laplacian equation. Nothing much to do here. You might be asked to find the electric field and the potential using this Laplace equation. Some questions are in the tutorial, you can go through that. Now moving on, we have work and energy, specifically in electrostatics. So let's see. Let's suppose there is a static charge distribution. Let's say in this case there is a discrete static charge distribution. Static in the sense they're not moving anywhere. And you have some test charge capital Q which you want to move from point A with position vector A bar to point B with position vector B bar. What is the work done to move this test charge from here to here? So it is given by this work done against the electric field to move test charge capital Q from A to B. So why against? Because the electric field is not doing this work. Who is doing this job? You are doing some work. The electric field is not moving this charge from A to B. You are applying some external force to move this test charge capital Q from A to B. So that's why it is written as work done against electric field. That is the convention. So if it is against, then it is the negative of. If you look at this, force due to electric field is the opposite of force against electric field, and this is what we are applying. We are applying some force against external field. This is the external force against external field. So anyways, work done against electric field is nothing but work done formula, force bar dot dl from A to B. Force against is nothing but minus of force due to electric field, and force due to electric field is, we know, uh, force due to electric field on capital Q is capital Q into the electric field. So I'm substituting that here, you'll get this one. And I know that electric field is nothing but the negative of the gradient of the potential field over there. And if I substitute this, minus minus will get cancelled, I'll get this one. And then I can use gradient theorem now. If I use gradient theorem, I'll get this one. B at B minus V at A, final minus initial potentials. This is potential difference anyways. So there is no uh, this is true for any path because the final answer is only dependent on the final position as well as the initial position. So work done is path independent. Fine, beautiful. This is everything about work done. Now we'll try to see what is the work done to bring a charge from infinity to some point with position vector r bar. It's the same thing, but then we are bringing it from infinity. So our starting point is somewhere at infinity. A bar is infinity. Potential at infinity is 0 because you're so far away from your charge distribution. There is no effect of your static charge distribution on that point. So if your test charge is somewhere far away, there is no effect of this electric field on that test charge. So that's why the potential is 0 over there. And the final point is r bar. So instead of b bar, I'm writing r bar. So the same thing, work done against electric field to bring a charge from infinity to r bar is just this one. Instead of b, you have r, and potential at infinity is 0. So you have q into potential at r bar. Nice. So with this information, now we'll be able to find the work done to assemble a charge distribution. In this case, it is a discrete charge distribution. Let's suppose in the very beginning we bring a charge q1 from infinity to r1 bar. There is only one charge here and there is no electric field, so you can simply bring a charge and do no work there. There is no interaction whatsoever. So work done to bring one single charge is just zero. You have no interaction there. Let's say you bring another charge q2 from infinity and you place it at the position place it at a point with position vector r2 bar. Now this q2 is, it can't come simply like that because there is some electric field due to the static charge q1. Static in the sense it's not moving, it is fixed over there, it's not going to go anywhere. So when the charge q2 is being brought from infinity to r2 bar, it experiences some force, repelling force, but you still bring it here, so you're doing work against electric field. And we know what is the work done to bring a charge from infinity to a certain point, which is nothing but q into the potential, right? Here the q, capital Q is q2, and the existing potential field is this one, kq1 by the separation vector, the magnitude of the separation vector. This is separate, the distance of separation is mod of r2 bar minus r1 bar. Mod because distance is scalar and this is a vector, so you need mod over there. Anyway, so total work done is nothing but the work done to bring charge q1 and the work done to bring charge q2, and the rest is, it's the same thing. If you bring another charge q3, there is electric field due to q1 as well as electric field due to q2, and by the principle of super imposition, I can just add the two potentials. So this is my capital Q in this case. This is capital Q, and V of R bar is this big thing. V of R bar is V due to Q1 and V due to Q2. So work done in total to assemble this discrete charge distribution of three charges. It's W1 plus W2 plus W3. Let's say you have n charges and you want to assemble n discrete charges. What is the total work done? If you look at it, it is given by this big formula. After some simplification, it turns out to be this formula. What does this mean? You just find the summation, half of the summation of charge multiplied with the potential experienced by the charge due to all other charges. That is what this means. I hope the notation is clear. For example, I mean, you can look at it by yourself. There is nothing much, but that is in the case of discrete charges. In case of continuous charge distribution, my Q will be replaced with dq. So summation dq will be nothing but integral of volume charge density into d tau. So it's the same thing. After some simplification, you'll get this big thing. What is this big thing? Why did this become zero? You can go through it by yourself. Uh, if you if you look at the region of integration, I've written all space. Wherever charge is there, my volume charge density will be non-zero. Wherever my charge is not there, there my volume charge density will be zero. So this is a valid region of integration. There is no problem doing this. Now, if you try to look at why this is becoming zero, I said the region of integration is all space. I mean, how did we get this? You can look at the derivation, but I'm trying to tell you why is this becoming zero. The region of integration for this volume is all space, and this is a surface integral, a closed surface integral, which is nothing but the boundary of all space. See, all space is nothing but entire space, and what we want to do is you want to do surface integral across the boundary of all space. There is no boundary to space, right? Space is like it's very big. For example, if you take a small cube, its boundary is nothing but it has six faces. But if you expand that cube to like infinite dimensions, if you take the entire universe, there is no boundary, so that will become infinite or something. So the reason they gave was, in order to conserve the value of w, this has to become zero. So that was the reason. I don't have a rigorous reason, but this is the reason that was given. So finally, this is the answer. The work done to assemble a continuous charge distribution is this one. If you do this, you'll get your work done due to a continuous charge distribution. Oh yes, we have nothing much, nothing left either. So this is work and energy in for electrostatic fields. That's it. We are done. Thank you.